Welcome to Oddly Real. I'm Nem Stefanovic. We live in an amazing age of machine intelligence. Traditionally, computers have specialized in following given instructions in the form of a computer program to perform calculations, compare values, operate hardware, and various other tasks. These are very coarse, high-level actions that direct a computer to do something in a step-by-step fashion. Yet, this approach doesn't work well for perceptual tasks that a human being might be able to do, but can't quite break down into steps. In fact, a human being may not even fully understand how they do it themselves. For example, human beings are able to recognize individuals by looking at their faces. How would we direct a computer to analyze a digital image to distinguish between any two human beings? There might be some human characteristics like eye color, nose shape, or facial hair that are more easily distinguishable, but many individuals could fit this same profile. Human beings possess many subtle physical characteristics that other human beings can innately recognize, but can't be captured adequately by a handful of broad rules. Moreover, it's not even straightforward how a machine can identify a human face out of a picture at all, given backgrounds and other foreground components, let alone how that face might be different from other faces. In order to solve perceptual problems like this, a machine would need to consider many more fine-grained, low-level details within images. Facial recognition problems and many other perceptual problems are better suited towards machine learning-based architectures like artificial neural networks, rather than traditional programming logic. These kinds of systems essentially do the opposite of what traditional computer programming does. Normally, we would provide the instructions or rules for a computer plus some data, and the computer would use those to generate output. Instead, machine learning works by providing a system with examples of outputs that we want, and some general guidelines to let the machine figure out the rules to reproduce the expected results. A facial recognition system may be trained with many examples of faces to be able to distinguish their various features. Neural networks were roughly inspired by biological neurons in the human brain. They are relatively simple computational units that are able to work together in parallel and in large numbers to solve perceptual problems. Examples of perceptual problems include speech recognition, music classification, letters and numbers from handwritten notes, and medical diagnoses from medical images, among many others. The fundamental units of neural networks are the neurons, or nodes. Each node accepts multiple inputs and produces an output. Each input consists of a real number value and a weight, which is also a real number. The inputs are multiplied by their weights and summed together to produce a total. That total can simply be the output of the node in the case of a linear node, where the linearity is called a linear activation function. This type of node tends to be too simple and can be demonstrated that linear nodes in a neural network can be collapsed to an equivalent single linear node. So instead, neural networks will purposely introduce a little bit of nonlinearity into the node through an activation function that is essentially the same, but rounded to zero if the calculated value is negative. Any number of different activation functions may be chosen for the design of the neural network. The architecture of neural networks consists of nodes arranged in layers that take inputs, pass them forward through the layers to the final output nodes. The output nodes each represent a different classification that the neural network recognizes. For example, you could be classifying 3 different plant species from pictures where each output node will represent one of the plants. Each output node produces a value that indicates the degree of match to that class. The layers of nodes prior to the output nodes are referred to as hidden layers, since they essentially act as intermediate calculations that support the final results. There can be millions of these nodes. You might have heard the term deep learning be used to describe neural networks. This is actually a fairly loose term to suggest that there are many network layers that process large amounts of data. There isn't a specific number of layers that qualify as deep, just that there are many. The outputs of any given node are passed forward and not fed back to prior nodes to ensure that units aren't dependent on their own values. For example, if we're distinguishing between images that contain a human, cat, or dog, there could be 3 output nodes, one for each type, human, cat, and dog. Each node would compute a final calculated value to represent the degree to which that image matches its respective classification, human, cat, or dog. In this case, we can take an image that is represented as a 1024 by 1024 color pixels and feed each pixel's color representation, which is 3 values for red, green, and blue, into the neural network. This amounts to a 1024 by 1024 by 3, or over 3 million data points, representing a very granular input. These values would feed into the first layer of nodes, which produce outputs, and the results would then further propagate forward through the network to the next layer of nodes. Each forward propagation would also be multiplied by its respective connection weights. Once all of these values of the output nodes have been calculated, the computation stops, yielding the degree to which each class is matched. The real magic of neural networks is captured in the values of the weighted connections between the nodes. In fact, the architecture of a neural network and those weights, also called parameters, represent a kind of computer program. Traditional computer programs consist of individual command statements, variables, and comparison operations for flow control. However, we don't see any of those components in a neural network. Yet, surprisingly, it has been shown that we can represent almost any program in the equivalent form of a neural network using appropriate values for the weights. There are a few limitations. Since neural networks have a fixed number of layers, this puts a limit on representing a large number of computational loops that a traditional program might use to solve a problem. Additionally, representing smooth functions like a sine or a cosine function can only be approximated to a certain degree. However, given the low-level input nature of neural networks and the flexibility to represent almost any computer program as weights in the network, this is an astonishing capability. Neural networks are so flexible for perception-related problem solving that the exact same architecture can be used across multiple different problems as long as the weights are reprogrammed to solve for the specific task. For example, a network with one set of parameters could be used in facial recognition, while the same network with alternate parameters could be used to predict visual cues of fatigue or fear on faces. But how are the weights of the neural network chosen? We said that the neural network is supposed to figure out the weights of the node connections from our provided output examples. How does that work? This is accomplished through the use of a loss function. The purpose of a loss function is to figure out how far off the neural network's recognition of its classes are from the real classifications. In other words, if a neural network predicted an image was a dog relative to a human or a cat, how close was the actual numerical prediction? More specifically, how good is the classification process using its current selected connection weights across all of the provided training images? So what would an example of such a loss function be? This is not something unique and can be picked by the engineer. However, one common example of a loss function is to take the inputs for one example image and run it through the network to produce an output. Next, we look at the difference between the predicted output values for each of our classes and the actual class itself to see how far off the values are. Typically, we don't just look at the raw difference, since this can sometimes produce a mix of positive and negative values. Instead, we look at the square of the difference, which makes all of our values positive and easier to work with. Finally, we repeat this process for all of our examples. In this way, we can get a total overall value for our loss function that uses all of our training data using our existing weights in the neural network. So a loss function is a measure of how far off our neural network's recognition is from the examples that we've provided. But we still don't know how to actually find the right weights in our neural network to minimize this loss. Luckily, when we have a loss function defined, there is a technique we can use to leverage that function to pick better weights and improve the results of our neural network. We call this approach backpropagation, and it's essentially running the program backwards, starting from the output nodes back toward the inputs to iteratively adjust the weights in the network so that the loss function is improved for the downstream components. The weights can be shifted up or down to see if the loss score improves with the help of mathematical techniques like gradient descent calculations to predict how to adjust the weight. We can summarize the process involved to train the neural network by picking its weights to minimize the loss function and produce good output results for the neural network. First, we select our neural network architecture, which is based on the number of inputs we have, the number of classes we need in our output, and the number of hidden layers in between. Second, we start with random initial network weights in the network, since we don't know in advance what the actual weights need to be to solve our problem. Remember, machine learning is a process that will figure out those weights to program our neural network from our provided sample output data and our loss function. Those random weights are used along with our input training data to produce a set of final predicted results at the network output. Next, we conduct our backpropagation process to adjust the weights in the network to improve the output results by reducing the loss function further. We then repeat the backpropagation process until we find that we aren't improving the final results much more. It's common practice for machine learning engineers to divide their data up into two segments, where one segment is reserved for training data in order to set the appropriate weights. The other segment is reserved for testing purposes to assess the performance of the trained neural network. In fact, there are many techniques that can be employed in the process, and the one I've provided is really just one example for illustrative purposes. Finally, we can look at an example application of neural networks for identifying handwritten numerical digits. You might be surprised to hear that the US Postal Service has been using neural network technology since the late 1980s to help automatically sort handwritten mail according to its zip codes and addresses. This technology used neural networks to recognize the various handwritten letters and digits, which varied from person to person. Specifically, if we wanted to create a neural network to recognize handwritten digits, we'd need 10 output nodes, one for each number from 0 to 9. We'd also need many samples of human handwriting, perhaps thousands of samples. We'd want to use most of the samples to train the network, but we'd want to leave some samples data aside to help test the trained network afterwards. I hope you enjoyed this episode, and remember, oddly real, really interesting.